Okay. I'm going to assume that we have everyone. I'm going to close the door and you can start.
Good morning, everyone. Thank you for coming. We're super happy that again so many people are here. We just said we could indicate it. So today we'll be looking at deep learning. And actually, when we do workshops at MLT, unless it's like natural language processing, I'm not the one doing workshops. My team is doing workshops. And Mustafa already arrived. And Mustafa, as I mentioned yesterday, is a machine learning engineer.
Good morning, everyone. My name is Mustafa. So I've been living in Japan now 6 years, and I was working for a company, and now recently I started my PhD. And together with Suzana, maybe the last 1 year, I just organize events like this. Happy to see you today.
Thank you.
And I'm really happy because, Mustafa and Iris and Dimitris are going to join us today, and they are working, so they're going to come over and help us with. Mustafa is going to introduce convolutional neural networks and do some data exploration, and Iris will be doing a little bit of PCA and Tigging, what we heard about yesterday, and then Dimitris will walk us through the CNN pipeline, how to train a convolutional neural. Okay, so again, you can find the slides and notebooks in our GitHub repo, and right. And one more thing before I start, because yesterday someone asked me how to learn Python. At the end of the slides, at the end of the slides, I added a couple of tutorials, which is like Python for data science or Python for machine learning, just like kind of a couple of hours. So it's a really good intro to learn how to write code for data science. Also, we had a really interesting discussion yesterday about domain experts in deep learning. And I was thinking, I'm active on Twitter, and there's a huge machine learning community, and I asked, so how important are domain experts in deep learning? And I think almost 500 people answered in a few hours, and they said 5% said not important at all, 24% said somewhat important, 55% said very important, and then 16% said it depends. I think this is a pretty good depiction of real-world use cases, because in fact you might not need to be a domain expert to just train the model. You can just, if you know data well enough, if you know machine learning well enough, you can prototype very easily and just build a very simple machine learning or deep learning model, build your machine learning expertise. Also, like when we see Kaggle competitions, we see that the guys that are leading, that are winning the leaderboards or leading the leaderboards, they're typically not domain experts. So those people are really, really good at engineering, at applied math, at thinking about a problem, how to do feature engineering and things like that. And if you look at the comments, I don't know if my Twitter handle is here, but so a lot of people commented actually explaining how domain experts are really important. And domain experts are important in cases where we have to define a problem statement, right? Where we have to define the task. What are we talking about? And of course, we know, as I mentioned yesterday, the data very well. And a lot of people have answered and commented on that tweet, sharing like experiences being a domain expert in machine learning, or what kind of fields would benefit from domain experts. Like one person answered, I think it depends on the accessibility of the domain. In particle physics, the Higgs Kaggle challenge, there was a Kaggle challenge, showed that a physics degree wasn't necessarily required to win, it wasn't required to win at all, but actually using the model in the proper analysis needs a full understanding of experimental and theoretical uncertainties. So if you want to go beyond like a feature engineered model that wins your Kaggle and have it as a research project or deploy it in industry, I think domain experts are really necessary, and that's probably consensus. So I would say like 20, 60, maybe around 70, 80% would say domain experts are. Okay, so let's dive into neural networks. This section, I have only 45 minutes, maybe even less than 45 minutes. So this will be like a very intuitive, very basic high-level introduction to neural networks. What are neural networks? What can we use them for? In what kind of scenarios? And answer maybe a couple of questions we had yesterday. And this kind of conceptual explanation will be followed by some code. So we'll be doing some data inspection, just kind of looking at our data and explore a little bit, look at the size, look at class balance or imbalance and what to do in those situations, and then train our first convolutional neural network after the break, after the lunch break. So today, after lunch, we'll be working with this data set. This is a Kaggle data set. It's a multi-class classification test. So we're basically having these images, and we have 6 classes, and we're trying to build a multi-class classifier. And it's a 28 by 28, so it's very low resolution, which should make the problem relatively easy. And interestingly, we have 4 channels here. Typically, we have 3. We have RGB and this add Hammer channel as an infrared. Just kind of FYI, but we will dive into this later on. So when I say deep learning, I refer to end-to-end learning from complex patterns, from data with complex patterns. In high-dimensional space, we're talking about mainly data such as I mentioned yesterday, images, text, audio, video, and so on. The good things about deep learning is that we don't need any feature engineering. So in theory, you could do, I mentioned this yesterday, we see sometimes hybrid systems, feature engineered systems. But in theory, it really kind of automates this manual human process of feature engineering or hard coding away. So we just feed our input data to our end-to-end system and get our outputs. It is great for computer vision and natural language processing, and deep learning architectures achieve state-of-the-art results for many, many tasks in these areas. The downsides of neural networks are that they require a lot of data. Typically, they don't work very well with small data sets, even though there are techniques how you could work with small data sets. Nevertheless, using things like pre-trained models or transfer learning. But generally, deep learning performs very well when we have large-scale data sets. Another downside is that it requires a lot of time to train and a lot of computational power. So we saw yesterday when we looked at classical machine learning algorithms that it literally takes one line of code in scikit-learn to fit classical machine learning algorithms such as the support vector machine to our data. And it also takes no time. This would change if you would have like a larger data set and you would do something like grid search to find the optimal parameters. So this would take maybe a little longer, but in general, it's very fast and it's very simple compared to training a deep neural network. Also, we saw yesterday that we really don't need a GPU. We can fit the SVM just perfectly fine on the CPU, but we do need a GPU for deep learning. Well, we don't. We can. So sometimes I train deep learning models on my Mac. But I work with text, which is not that heavy. I work with smaller data sets, so it's kind of okay. But still, like if you train it on GPUs, it will speed up things, and that's generally a good thing. The other thing is that it's relatively difficult to find the optimal hyperparameters. So we saw yesterday we have algorithms in machine learning that have certain parameters, such as the SVM has something like a C parameter or a gamma parameter. In deep learning, we also have parameters, but we also have hyperparameters, which are very sensitive, and it's very hard to tune them to stabilize your network so that you really converge very efficiently in a very fast way. So this process can also take quite a long time. Again, like here, we also have methods like grid search and random. I would recommend grid search with random search or Bayesian methods. But yeah, these things just are very time consuming. And to design the optimal architecture is a difficult thing. So when we say deep learning and deep neural networks have achieved or are still achieving like state-of-the-art results in machine learning research, we might think that these algorithms are super new and something cutting edge, but in fact, some of these algorithms are super old. They've been around for decades, in fact. If we take a look, I don't know if this is big enough, but if you take a look, so backpropagation, which is the main kind of core algorithm underneath like deep neural networks, was invented in the 70s. And then we see like multi-layer perceptron, a feed-forward network was also introduced in the 80s. We see algorithms that achieved state-of-the-art until recently. LSTMs and bidirectional LSTMs were introduced quite a while ago. And then we see like newer architectures like generative adversarial networks in 2014, sequence in 2014, and so on. So some of the algorithms and some of the concepts are actually pretty old. Now, what changed everything and what made deep learning successes possible, it basically comes down to three things. First of all, we have access to large-scale data sets. This definitely wasn't the case like 10 years ago. We have access to large-scale labeled and unstructured data, which is great like for supervised learning as well as for unsupervised learning. We see really amazing stuff coming up in all kinds of areas, most recently probably in the area of NLP, where we have GPT-2, the GPT-2 model that was trained on an enormous amount of unstructured data with very complex architecture that really generates pretty amazing results for natural language. Also, data collection is easier, so we have a lot of different ways how to get data, how to get unstructured data as well as labeled data. There are services out there like Mechanical Turk. It makes it very easy and very cheap to get labeled data, as well as data storage. So the infrastructure plays actually a really big role. Infrastructure and compute, so we have access to GPUs. So we have either access to GPUs as hardware, as you can see here. I think that's probably the monopoly provider for hardware. But we also have access to GPUs in the cloud, which makes it possible for me with a Mac to just access some cloud GPUs and train my deep learning models there. And of course, I mentioned algorithms. So some of the main algorithms are pretty old, but machine learning research is very, very active. It's very competitive. Thousands and thousands of papers are being submitted to each machine learning, to every machine learning conference. And so progress here is competing for state of the art and for benchmarks. So progress here is really great. The other thing that we have is really great frameworks, tools, and APIs that make things really easy for us. So this was definitely also not the case just a few years ago. I mentioned some of the frameworks yesterday, so this I did, and I also mentioned that the barrier to enter the field is very, very low. So these things really kind of made these breakthroughs in deep learning possible. So yesterday I talked a lot about data and tasks and how these things kind of influence each other, and how they determine our decisions in terms of how do we choose certain architectures or algorithms. And today we'll be going a little bit deeper into algorithms and architectures for neural networks. So we will be focusing today on convolutional neural networks. So I will just briefly mention RNNs. I think most people maybe don't work with sequences except for you. So mainly we'll be maybe working with computer vision today. And because this is also the standard intro kind of, the first thing you do probably when you get into deep learning is build an image classifier. There's a lot of things that you can do in deep learning for computer vision. So we already seen classification tasks where you have a couple of categories or two categories, and you're trying to classify the correct class. Then we have things like object detection, where you put these bounding boxes and detect objects. There's something called semantic segmentation, or also instant segmentation. So these have different kinds of application areas. Some of those we see for self-driving cars, but there's many different application areas. And another thing that I found yesterday, kind of by coincidence, when I was browsing through Kaggle for our data set today, is, and this was published five days ago by Keio University. It is an artificial lunar landscape data set. So this is artificial, it's not real. And they, I think they open sourced almost 10,000 of these images that are, so this is a good example for semantic segmentation. So basically they segmented, what is it, like the sky, then smaller rocks and larger rocks. And the reason why they created this artificial, so basically you see in research we can do all kinds of stuff. So not only annotating but also creating images and kind of. They created this artificial data set because we don't have enough images in that kind of field. And now they're looking for feedback. So it was literally published 5 days ago, and they have a data set of 20,000. And first they need to collect some feedback. So if you're interested in that kind of direction, there's the link, and they also published a kernel, so some code where you can experiment and take a look of how they constructed the data set and also the annotation. So as you see, like things like annotation, yeah.
I was just going to ask, so like, even though it's an artificial data set, it actually helps train these algorithms to recognize rocks and the real images? Or...
Yeah, that's the question, right? So that would be the goal. I think you see this quite a lot actually well, you see it in industry a lot, where people use generative models to artificially create more training data. But this is not real data, but it is good enough to serve as training data. So in this case, yeah, so the goal is basically to create this artificial data set to be able to train on real data. Not on real data, but to test it on real data, to have more data. Yeah.
Yesterday, I think you or Nick showed some sort of data bias for the Chinese.
Yeah. Yeah.
How about this one? Because this
bias?
Would there be some kind of bias? Because this is artificially generated, right? So it means the people that made these images have some kind of bias against it. Right?
Absolutely.
So then, I mean, that bias is inherently.
I think so. And bias is not something that we'll be talking about in the bootcamp, but I think maybe we should, because it's an incredibly important topic. So when you construct data sets, you will have to be very, very careful. Obviously, it depends on the domain, right? So some cases, I mentioned yesterday, some data is very sensitive, right? So you have to be careful in many different ways. And they can also carry inherent bias, right? When you collect large scale, automated, if you have automated ways of collecting large scale data, you need to make sure that you're at least aware of the bias. So, and try to reduce bias as much as possible. I was a little bit, so a few weeks ago, I think I saw, I mean, this is a really difficult topic, right? I think we're all aware of it, and we need to find like proper tools and methods how to avoid bias in data, in systems, and so on. And there's, so mainly I see talks and papers where they're stating the fact, right? So we see, okay, we have bias in this data of these sorts. I see, and this is a question of like ethics. What I'm missing kind of currently is to really, so we need to work on that really heavily and to develop tools and methods that allow us to construct data sets and have as little bias as possible, or at least be aware of the human bias that a data set contains. But this is something that is in progress, and we need to work on that.
I should have been more direct. So is it theoretically possible from an informatics point of view to actually generate an unbiased data set? Because the people that are going to use this data set, the scientists that actually use this data to analyze their own data, have to be responsible. Okay, we know this is biased, and that's their responsibility. Right? But then, from the viewpoint of the people that make such a data set, why is it important to make such a data set with bias? Right? Is it theoretically possible to have such an unbiased data artificially created?
That's a good question. I don't think so. I don't
If
know.
not, what's the objective of
I think, yeah, so that's why I said we need at least to be aware of the bias. And so sometimes I wouldn't even call it bias because, well, it depends. So this image data set, right, it was artificially created and it doesn't involve really humans, right? So at least it's not that sensitive, right? Just a second. But maybe because it was artificially generated, it has like some sort of point of reference, right? So it will show some rocks, and this might only be a snapshot of the real world, right? So they have 20,000 images. I don't know how much you guys know about the moon. I don't know that much. But this is probably, yeah, these are things that we need to figure out, right? So what is this data set actually representing? So yeah.
Yeah, I think maybe a more direct, I think there is actually a more direct answer to your question in this particular case, because this isn't a situation where we have no moon data, right?
Yeah.
So what you could do is you could train on this, but then have the test set be entirely from real photos. And then that way you validate what you did. And my expectation would be this wouldn't work as well as if you tested it on the synthetic data, but at least you can check. Right?
But if you validate on the real data, you still have to manually check to see if it's actually doing things.
Well, the validating on the real data is the check, right? So when I get a score from a given distribution, what that's saying is that if I have enough samples to have a statistical, to have a confidence range or something of what that error is, if I were to go and put this in that circumstance again with the same generating process, I could expect that my error would be the same. So how I train it doesn't actually matter, but how I test it is really what matters. And in this case, you could still test this against the real world. And that would be just as good as having some arbitrary model trained by, picking numbers out of a hat and testing against the real world. It's not different in that sense. So it's the same, it's the apples to apples comparison. The other thing is that, even let's say we went a bit further than that, and this was really terrible when I applied it directly to the moon, which it probably would be.
You did?
No, I said if we went further
okay.
and it was really terrible when I applied it directly to the moon, which I think it probably would be, it would still be a better starting point for training on a small amount of real data than if we had to train the entire thing from scratch on only real data that we don't have much of. So as a pre-training method, this is also something that people do. They use synthetic data to pre-train and fine-tune on the real data. And those are both ways that kind of allow you to at least control the bias.
Yeah. The problem is that, so if you validate it on the test data, it will give you a score, right? So that's probably not enough. And that will not tell you what's the problem or what is the problem and how to find the problem in your data. So you need to do more than that, I'm afraid.
Well, I think it tells you at least if you were to use this, what would you expect to happen, which is the thing that matters. And if it turns out that validation score is 99% accurate and you're fine, you're probably fine. And if it's 10% accurate,
Probably not.
if you're 10% accurate or something, then maybe you're in trouble.
Yeah.
Or well,
But it's the first indicator, but it's definitely not enough probably to get to the root of the problem. Okay, I have 50 more minutes and this is my third slide. We have to speed up a bit. All right, if you want to try it out, go to Kaggle. So supervised learning, we said yesterday, mapping input to output, right? So this is the example of the MSD Hammer digit. So on the left side, you can see this is our input X, and we have our labels Y. So each handwritten digit gets a label. In this case, we have 10 digits, 10 labels. So we have a multi-class classification system. And the way you could look at neural networks, we have a couple of different ways how to look at neural networks. And I will briefly show you maybe just a peek of everything. So I think this image is very, very popular. When you Google deep learning, you're probably going to get something like this. What this shows us is an input layer. We have two hidden layers, an output layer, and the output layer is our prediction layer. So the first thing we do, we have our images, and these images are 28 by 28 pixels. So this input shape gets fed into our input layer, and we see all these neurons. And then we do some mathematical operations, and then we receive our first predictions, our Y print. And luckily, we have our ground truth. So what we do is we compute the loss. The loss is basically just a mismatch between our true labels, our ground truth labels, and the labels that are network predicted. And depending on that number, we do a couple of other operations. So the first we do a forward pass, obtain our predictions, and then we do a backward pass and update the parameters. And we do this in cycles. So this forward pass and backward pass, we do as many times as it's needed to kind of reach the minimum loss. So our objective is to update, to find the optimal parameters, to update the parameters, and to find the minimum of the loss. What's happening in a neuron is, so in the most simple form is, you can see that we have our inputs x, and each input x has a corresponding weight. We take the weighted sum of x and the weights, and we add a bias to it, and push it through a nonlinear activation function. So that gives us some nonlinear complexity. And that's basically all that happens in a neuron. We have a lot of neurons in a feed-forward network. Those are some of the most commonly used activation functions. You're probably all familiar with those: sigmoid, canage, or ReLU in different kinds of scenarios. And the weights, so the parameters, the weights and the bias are very important for the learning of the network. So as I mentioned, our goal is to find the optimal parameters, to find the optimal weights. So what we do when we initialize when we start our network, we can initialize our weights randomly. That means at the same time, the first predictions we get are probably going to be very terrible, right? Or nonsensical, because it's randomly initialized. What we can do is do something like we can incorporate pre-trained weights. I have here an example from natural language processing where we could use something like love embeddings. Those are word vector representations. So this was a model that was trained on large amounts of unstructured text, and it gives basically the Euclidean distance, or the user Euclidean distance or cosine similarity to show like the semantic similarity between two vectors in the space. And those weights you basically save and you incorporate. You put it as initial weights into your first layer of the network, so it already has a sense of meaning, right? So you don't completely randomly initialize. It already has some sense of meaning. Or you can do things like transfer learning, where you transfer different models. Pre-trained model is a safe network that was previously trained on a very large-scale data set. So this is typically maybe not the exact same task that you have or data that you have, but similar enough that you could use it to infuse some first information to your model, and this typically helps a lot. So how does learning in deep networks happen? So first of all, you never feed your whole data set into your model. You feed it in batches. This is like the more efficient way to do it. So first of all, you draw a batch, you draw a mini batch, and then you feed your inputs X into your model, as I already said. You train your network. We already went through this again. This already. We do a forward pass and we obtain our first predictions. Now we compute the loss. I mentioned it's a measure or it's measuring basically the error between the things that we predicted and the things that we should predict. And what we want to minimize is the loss. And here you can see two different depictions of the loss function. Obviously, this is not in a real. This is just a very simplified way of explaining how the process of learning and gradient descent is done in networks. Of course, we work in very high dimensional space. But you have here a 2D and a 3D, and the lower one, it's like a comparison when we have a convex loss function, which we never have in the non-convex function. And this non-convex loss function sometimes makes it hard to find really the optimum minimum. It can get stuck. It's like there's many ways like how you cannot reach the minimum. But the objective is to find like really the lowest point of the loss function. So you have your basically your predicted values and your ground truth. You compute the gradient of the loss, with regard to the network's parameters, you do backward pass, and you update those parameters. You update those weights, and then you train again. So this is basically like a whole cycle of neural network training. And the objective is to update the weights and to reduce the loss as much as possible. So there are, I mentioned there are many hyperparameters in the network, and all of these hyperparameters that you see have some sort of effect or impact on a lot of things in your network. So for example, how deep you're going to build your model. Like how many hidden layers is this model going to have? What is the number of hidden units? What is the number of neurons? These two things especially have also like a very high impact on your training time. If you have a very deep model, if you have a lot of neurons in each layer, is going to take a lot of time. How you initialize your weights. So these are very important choices you make if you're going to randomly initialize, if you have some sort of pre-training. The batch size, like how big is going to be how big are going to be the batches that you separate your data set to? What kind of activation functions? Typically, when we talk about things like LSTMs, you'll see later on, there's already like a built-in, like things are already built in, so you don't have to worry too much about this. What is the number of epochs? When do you know how many cycles do you actually need? There's like different kinds of techniques that you can incorporate, like callbacks, that will monitor your validation loss and stop the training when it reached the minimum loss on the validation set. Things like the learning rate. So the learning rate is kind of the step that you take when you have your loss function here in 2D, and you kind of incrementally, step by step, move towards hopefully the minimum of the loss function. How big is that learning rate going to be? If you choose it to be too big, it's going to kind of look something like the one below. If it's going to be very, very small, it's going to take a very long time to converge. So these are very tough decisions. Also, things like the optimizer, you have to choose how the weights are updated. Then you could do things like to regularize the network. Like what we want our network to do is to generalize really well. So the patterns that it sees in the training data, it should be able to take this and to generalize over any test set. So this is the objective. And what we want to avoid is that the network memorizes the training data. And there are different techniques how we can actually avoid this kind of overfitting, which could be a dropout, so you kind of randomly deactivate activations in the network, or do other things like L1, L2 regularization. In order to find these optimal hyperparameters, I already mentioned you can use different kinds of methods. Yeah, we might don't have enough time to go into this. Okay, so another way to look at neural networks is just to look at code. And as I said yesterday, probably the easiest way to get into deep learning is just to start writing code. There are benefits to this, and there are also drawbacks. So here, basically, so the pink ones are just comments. So 1, 2, 3, 4, 5. The compile you can actually write in one line. With 5 lines, you can basically write a neural network, a very, very simple, fully connected multi-layer perceptron, and fit it in another line. So in 6 lines, you build your neural network. It's not that deep, but it's deep. We have a couple of hidden layers. It's not that deep, but you can see you can write it like in very few lines of code, and it's very clear, right? It's very straightforward. We see the layers. We see a dense layer. A dense layer is a fully connected layer. Basically, what I showed you in the beginning, the neuron that I showed you in the beginning. We see the activation function, a value, a nonlinear activation. We see the input shape. We see the number of neurons, right, 64. And the last layer is actually our prediction layer, right? It's another fully connected layer. And the 10 here indicate the number of classes. So we see, okay, this last layer is our prediction layer. 10 is the number of classes. The activation function in the last layer tells us also a little bit something about the task. If we have a softmax on a 10 class classification system, it will give us, so the thing that it will return is basically 10 different numbers, right? It will give us probability distributions, 10 different probability distributions that add up to 1, that sum up to 1. And the one that is the highest is the most probable to be our predicted class. In Keras, we have to compile our models. You don't have to do that with every framework. In Keras, we do. So we have to choose our optimizer, our loss function. Generally, you could probably use any loss function. We had a workshop of loss functions. You can write your own custom loss, and our metrics. And if you look at those numbers, right? Okay, so we have an atom optimizer. It says default is 0.001. We have a loss, a categorical cross entropy, and we have accuracy, and also like how to choose the number of neurons. These are like difficult questions, but those are default values. So you can either refer to papers, for example, that achieve state-of-the-art results and replicate those papers in terms of numbers. So these are large-scale experiments that basically find out the best way how to construct a network. Or you start with the default numbers and do something like a random search. And lastly, you fit your model, you train, you set your data and your labels, you set your epochs. This is 10 epochs, so we're gonna train in 10 cycles. The batch size is set to 32, so we'll feed our network 32 examples per batch. And then we train a model, receiver accuracy, and evaluate. Now, yesterday someone asked, how do we know which algorithm to use, right? If we have no idea, what should we do? And there's a lot of things that you can do. First of all, look at your data. What are the properties of your data? Are you dealing with sequences? Are you dealing with images? And the second thing is look at different algorithms and what are the properties of the algorithms. For example, images are objects of fixed size. So we have fixed size vectors. We know fully connected or feed-forward networks or vanilla neural networks, however you want to call them, take fixed size objects and give you fixed size objects in return. On the other hand, we have sequences such as text or speech or things like that are of variable length. So we need a network that is able to capture variable length sequences and maybe also process and memorize temporal information. Now the question is, can you classify images with a vanilla neural network or a recurrent neural network? Yes, you can. Is it the best choice? Maybe not. But in theory you can. So I added somewhere a link, I think, where you can classify MNIST with a vanilla neural network. And I'm running out of time. So we're not going to focus on RNNs today. If someone is interested in RNNs, we're going to later talk about what would you be more interested, what would you need for your task, and so on. The good thing about RNNs is that they have a sort of memory and different variants of a recurrent neural network. So this looks maybe similar to what we've seen before, with the difference that we can, at each time step, we basically store a hidden state in addition, and we pass this on to the next kind of time steps. This allows us to memorize information over longer sequences and to store temporal information, and this is exactly what we need for sequence models. A couple of examples of recurrent neural networks and what you can do with them. On the left, you can see this is a vanilla neural network. It takes a fixed size input and it gives you a fixed size input. An example would be to take as an input an image, a fixed size, a vector of fixed size length, and it gives you as an output a number, probability distribution, a class. It's a cat or it's a dog. The second is a one-to-many, which is a fixed size vector as input and a variable length sequence as output. So this could be for example, you feed it an image, so a fixed size vector, and what you receive is a caption. You receive a piece of text which is of variable length. So you see what Nick mentioned yesterday. There is a certain flexibility that we have with neural networks. So yeah, there are a couple of other examples where you have variable length input with variable length output. For example, neural machine translation or chatbots, and so on. So the other thing is how to choose that algorithm, how to choose your baseline. And there is no recipe for that, and there is no easy answer for that. This is something that is always changing. 2 years ago, my baseline was a support vector machine, and then I built like state-of-the-art LSTMs on top of that. Now, I maybe would build my baseline as a single LSTM, and then build on top of that. There are also other architectures such as sequence-to-sequence models for sequencing, or sequence modeling, where you have an encoder-decoder system, as I just mentioned, where you have neural machine translation. This is also already outdated with transformer architectures that just take like a piece of technology that was invented called attention and build like fully connected layers that fully rely on attention mechanisms. So this is something that always changes, right? But what's never going to change is that you know your data, you know the properties of your data, and you know the basic properties of algorithms. Oops. Okay. Oh, first that. All right. So that's it as an like intro to neural networks, and Mustafa will now take over, and he will explain a little bit about convolutional neural networks. Then we're going to write a bit of code, and then after the break, we'll write some more CNN code. If you're interested in what these kind of things are, these are very, very famous convolutional neural network architectures. I added like our repo. We had a really super popular workshop on CNN architectures where we go through all of the famous architectures, and you can find the code of them too if you want to see like what more complex things look like. Okay.
It's not USB.
Oh no.
What about this? Yeah, this is yeah, it's not the side. Okay, usually on this one.
Yeah, I had trouble yesterday as well. It took a while. I'm not sure why.
Yeah, that's it. So other German slides.
It's called, right?
Yeah, well, yes.
I do have this.
Could you guys start with slides and we can give a break?
Oh yeah, that sounds good. Yeah.
That's mine. I already edited. It's only.
You can close it if you want to.
Okay, well, I will begin. So we have around 15 or 20 minutes of slides before like intro to CNNs, and then we give a break, that 5 minutes, and then we continue the data part, the exploration part. Yeah, first of all, yeah, Suzana just really very nicely explained all the theoretical background of these like neural networks, all the like components of neural networks, all the learning process. In this slide, I just touch some like computer vision topics, and then let's show some like, visual stuff to realize and to more to understand more really how it's going, how the CNN architecture is handling with images. So yeah, we start with computer vision, just a simple intro. As you know, computer vision is a field, not image processing, it's... Ah, yeah, okay, so. Computer vision is a field handling with images, videos, first like extracting some features and then learning those features, and then detecting something, for example, just sensing the image, what content it has, person or like cars, any. There are lots of actually applications in computer vision. So it's not only the extracting features, it's also learning. So we have like two parts: one feature extraction and one a class part. I mean, learning part. Today, actually, we all like talk about the images because this workshop is based on images, satellite images. That's why we just start from this part. Yeah, let's go. So, what's the goal? The goal is just extracting meaningful features from images. What we have, for example, we have this kind of image. Actually, it has lots of information. So what kind of information is like edges, corners, colors, shapes. So we want to extract those features from image, and then use in further steps to like understand what it has. For example, these bullets or this person or scene understanding. So we have algorithms for that. Like these are classical algorithms like grayscaling, thresholding. Or like complex algorithms like these Hawk, Sift, Surf. There are lots of hundreds of algorithms, all very like mathematical, like hardcore mathematical expressions. So it's really difficult to extract features, meaningful features from images. So we need to design special algorithms. So let's see here. So we have an input image, and then we have a feature extraction part, and then we have a learning part, like class part. Actually, feature extraction is also can be called like learning. So let's check this feature extraction. It's all like these all algorithms, handmade algorithms, handcrafted algorithms. They are really full hand of engineering, so it's very like hardcore math is needed for designing these algorithms. So depending on the algorithm, we can extract different features from image. But this is really, not a practical solution. So we need to design again and again a new algorithm for extracting different features from image. So what convolutional operations are doing, it's actually, solving this problem, making the computer vision great again. All these using convolutional operations, using along with neural nets. So this is the basic structure. We have an input tree. You can think like an image. So we have a feature extraction part and then classifier part. So in this feature extraction, we have like multiple operations, as Suzana explained. And then in classified part, there are like predictions, 0 to 9, because this is a very common example. This MSD Dataset. It all contains numbers, images as numbers from 0 to 9. So we have outputs to 0 to 9, and then one of these outputs will be our predicted output. So we expect at the end of this network 3, to get 3. Okay, well, so what's the convolution operation is basically filtering operations. We are just filtering images by using special filters, special kernels. Different filter or different kernel just extract different kind of information from images. And we apply, actually, convolution is, we all know actually, it's a mathematical operation. So in case of images, we apply 2D convolution. We also have 1D convolution. So it's another topic. We can apply the 1D on images because we have 2D, 2-dimension or 3-dimension of images. So we have a kernel, and then we just slide this kernel across the image, and then calculate all dot products between every number in kernel and every pixel in image. Let's see here. We have image and then convolving with a kernel or filter and getting a feature map. So this term is very most common term. You should memorize this feature map. We will all talk about these feature maps. We have image, we are convolving with filter, and then this filter is just sliding all across the image, and then we are getting specific numbers as feature map or features. So when applying, this is just one filter, we can apply thousands of filters, and then we will have thousands of feature maps in this case. Let's see if we apply different filters, different kernels. When applying, for example, these kind of filter, these numbers, these are actually special numbers. For blurring images, these numbers specifically used for blurring images. So we get a more blurred image. And if we apply these numbers, as you see here, we get a sharpened image. But if we apply these numbers, we get an edge result. Edge of image. Edges, all bullets. You can see all the person on edges. So here, the weights, these numbers we call weights, are all we want to learn about, all we want to update. So this is the very key point of learning in computer vision when using CNN architectures, convolution operations. You can try actually. I won't show here. So let's see. This is the person, image, input image, and we have this kernel. It's a 3x3 kernel, and as you see here, when we apply this, this is the kernel. This is kernel. This is our filter. This is for sharpening.
specific numbers for sharpening. So when we slide across the image, as you see here, we just get the different outputs, get these numbers, and then the output is like sharpened image. We can change. We can, like, for example, like filter, silver filter. So we expect some like edges again. So these numbers are really important for us. You can check out later this page. Okay. So so this is the input image, and we're convolving, and then we are getting a feature map. Okay, so feature learning. In convolutional operations, in CNN architectures, we have actually different steps of convolution operations. At every step, we are learning a different information because all the output is changing. In the low level step, we may have like these like edges and then colors. These are usually colors and edges together. Before that, actually, at the very beginning of this operation, we might have like some edges, and then we observe some colors. When applying again and again these filters, we may have edges, colors, and we may have like shapes and textures after applying many convolution operations. So that means at the very beginning we have simple like features, and then at the top of the at the end of the operation, we might have like these complex features like shapes and textures, and then we just forward these all the features to the classifier. Let's see here. These are network architecture. We have image, and then after applying convolutions, we are getting all the feature maps here. And then there's a special operation like pulling. It's resizing, kind of resizing, downsizing these feature maps, because here we have lots of parameters to learn. So if we continue like this, we will have like hundreds of millions of parameters which we can't handle actually. So that's why we need to apply some special operations as pulling. And then we flatten, and then just create to this classifier. Let's see here. Convolution operation is, these are components of convolution operation. Like kernel size, we need to define strides, which is like steps to apply filters. We need to also define heading. It's like when applying convolutions, we sometimes need to add some, for example, zeros around the original image to capture all information of image. And then this is the pulling layer. This is one example of pulling layer. There are different pulling operations. In pulling, for example, these are like this feature map. Let's say this feature map, and we just apply a 2x2 pulling, and in every 2x2 region, we are choosing a maximum value. For example, in this 2x2 region, we have 6 is maximum, and we get 6 here. And here, like 8 in green region, we have 8 maximum, and then we just take that. And then 3, and then 4 come in here. This is max pulling. So it's just taking the maximum value in that region. But there are other pulling layers like average pulling, which is just averaging these numbers. For example, averaging these green regions numbers, and then having like, I don't know, maybe like 6 or 5, and averaging these green region. And then we have a flattening part. After all these convolution and pooling operations, we all have two-dimensional features. So, but neural nets are like units. So we need to like feed every pixel, every information directly to a neuron. So then we need to flatten. We need to just change the like this two-dimension of feature map to a vector. As you see here, these numbers, output of pooling layer, and we are just flattening it into a vector, which is this. Each number is just an input to a specific neuron. And then, yeah, we are, after applying these, okay, this is classifier parts and the predictions. We are doing predictions. So let's say, okay, we input a dog, and then it flatten, and then we use a classifier, neural net. Actually, this is neural net. Until here, it was not neural net. It was a convolution operations, actually. I mean, yeah, all is neural net, but it's specifically convolution operations. So this is the classifier part, and then we have predictions. Like for dog, we have very nice prediction and very high prediction, and cat is very low prediction. These two predictions in total have to equal 1, because prediction is a probabilistic approach. So at the end, we will have 1 in total. So let's see how calculating loss. We have 0.9 for dog, and we have cats like 0.1 as prediction. But we have classes 1 and 0 and labels. These are predictions, these red ones. These are labels, true values. So we need to compare. I mean, how we are well predicting something. So for that, we need to compare our predictions with true values. So 1 minus, for example, you can use any simple like calculation by hand even, like you can calculate, just subtract these numbers. But there are more like complex, more generalizing like loss functions, more useful loss functions. Like here, for example, this cross entropy. Applying these all logarithmic calculation derivation, we will have a loss at the end. And then using these laws, this is the forward operation. So far I talked. So this is the backward operation, the bottom one. So we get these laws, and then we just backpropagate that loss to update our parameters. So yeah, this is just a brief history. This is convolution operation. Convolution nets are not recently invented. It's just like maybe 30 years of history it has. It was just introduced by this paper around 1990s, and another implementation after a couple of years. So this is actually the original convolution net, LANet it's called. So it has, I guess, 5 layers of something. So we have, as Suzana explained, we have now at the moment very deep architectures, very deep nets. So it's because the deep is better than shallow. This is, yeah, very early convolution. I mean, ConNet, 1990s is LANet. It's actually well predicted. These are each feature maps. Each are different, as you see here, because different filters are applied. And different filters extract different information. Okay, so this is the first part. I guess yes. 10 minutes. Good. Okay, so we have a break. I mean, if you have a question, I can explain. If you don't have, we can have a break and then we continue with data part. Yes.
When you propagate,
Mm-hmm.
what would be the most like efficient way to like change the parameter? Is there like an algorithm?
Actually, yeah. Backpropagation is not the only solution, but at the moment, it's the only solution. I mean, there are other solutions, but the most like working, well-working approach is backpropagation at the moment. But yeah, maybe in coming years, I don't know, maybe in 5 or 10 years, we may see other algorithms other than backpropagation.
Is backpropagation basically meaning that you're changing the weight of the input?
Yeah. Yeah, actually. So at the beginning, we have weights of like, predefined weights or pretrained weights, as Suzana explained. For example, let's say these are weights at the beginning, at the very beginning of the training. And then after completing the first epoch, we get a loss, and then we use that loss, and then backpropagate, and then update our weights. It's more like mathematical. You can show anyway, but I don't have the slide here. So we have a slide for backpro.
For backpack?
Mm-hmm.
This is not the right one. The next one? Yeah. No, that one. No, I mean, the right one. There are two presentations.
Mm-hmm. Yeah, after getting predictions, this is one. Yeah, this is this formula as you see here. This is the loss. So this is the loss. Is J of data. I mean,
Can you make it bigger?
yeah. So this is the loss. At the end of the one epoch, we get this loss. We also have parameters. So we just take the partial derivative of loss according to, I mean, with respect to these each parameters, each weights. And then this is actually called like, and then this is partial derivative of this loss, and this is called like gradient. And then we use this gradient, and then just subtract from the parameters at the very beginning we had, and then yeah, after subtracting, we are having new parameters, which is this the left one. So we are doing this derivation again and again. Yeah. Is there any question? Okay. Yeah, let's give a break in like 5 minutes.
Thank you.
You don't have time.
Yeah, 15 minutes. Let's try to plan the
So
because my keyboard is different than yours. Is it the right
It's ready.
Yeah, let's try again because I have a German keyboard, so I might be it's very difficult. Yeah.
This is working. Okay. Yeah, yes. I think yeah. This is my
Yeah, I have to do it. I could.
It's right on your, just in. It's just here.
In front of the podium.
Yeah.
I can tell you the password. It's the year, the month, and the days. Yesterday and today. Sorry?
I'm thinking of all the ways they could be misinterpreted, like, you know.
Yeah, but he already had a look, so he would know it was numbers.
Monday,
Wow.
Tuesday, yeah, right. Very well. Kanji. That would be a really
Strong
to do to visitors. Put the Wi-Fi password in kanji. Okay.
First installed in Japanese input.
Especially if it were like you know, a nonsense reading, so that it was intentionally designed not to actually be a word, but to just be the onyomi or something.
Yeah.
So, okay. Spend some time guessing what the combination means.
So maybe. Just and then explain. And then,
So if you have some links that you want to share,
so
okay. If you have some link that you want to share, there is a shared document that everyone can access, so you can put stuff right there.
okay, one second. So yeah, exploring data, because yeah, this is I think the most important, one of the most important parts for starting to design to analyze something, because yeah, all we need to know about data, especially in case of images. In numerical data, it's all statistics. I think to check many things. In images, we need to understand what kind of image we have. I mean, is that noisy or like lacking in number or something? In my personally, I just check hundreds of images when I start or something. Maybe hundreds of images, yeah, by just naked eye, and then see understand the problem I have, and then I decide to do, for example, all the steps which I explain now. Okay, so let's just start from our problem. What we have satellite data. It's pretty small images. Each single image has like 28 to 28 and 4. Is this the first time for working on images for like most of us, or?
I think so, probably, yeah.
I see. For example, this 28 and 28, I think we can understand, right? It's like the size of image. And 4 is 4. Yeah, it's channel, it's or band, we can call satellite images. Normally we have RGB images. All we like capture by phones or like cameras, all RGB images, which is a 3-channel. And yeah, most of people are working on 3-channel images. In this data set, they use 4 channels, one more channel. I explain again. And you can have 1 channel as well. It's like grayscale image. If you have 1 channel, it's grayscale. I mean, only white and black, or gray. Yeah, the channels are red, green, blue, and near infrared. And training samples, pretty much training samples we have. Hundreds of images. And then test samples, which are given in CSV format. Normally, when you download the data, just directly download the images from internet, actually, and then you process that. But in this contest, I mean, this data set, they give in CSV file along with their labels. So classes from 0 to 5 classes. So mostly we start from 0. I mean, we have 6 classes actually. 6. But when designing our network, we just define the class 0 as a starting class, starting in the label. So we start from 0. Okay, so how a single image looks like. So this is an image of that data set. I guess it's like forest or something, or like a tree. Yeah, it's tree, because there's one tree. It's very small, and then it's very like, yeah, it's not so good actually. So 4 channels, 1, 2, 3, 4, and each channel looks like this. I mean, all pixels it has. So it's actually very similar to numerical data. In numerical data, we have all like numbers, right? In images also the same, I think. We have numbers, but in 2 dimensions. So we need to handle this 2 dimension and then make that 2 dimension at the end of the network to a vector. So each channel looks like this, all pixel values. And this, yeah.
So here, the both channels are infrared.
Mm-hmm.
So we assume that those all 4 channels have same resolution.
Yeah, I mean, because the same device are capturing these images, and the same sensor. And yeah, extracting features by applying filter. As I mentioned, when we apply filter to the original image, you will have like maybe edges like this. How it looks like in mathematical or this visual way. These are channels. Our channels we have RGB and infrared. 4 channels, and then so one channel is not seen here. Okay, this filter, and we have 4 channels of filter. So this is also an important point. If we have 4 channels, we need to have 4 channels of filter. Yeah, for language. If you have 3 channels, we need to have 3 channels of filter. And then we are convolving, and then getting this feature map at the end. One single feature. So this is just more fun, long filter. Actually, we have hundreds of filters in the operation. And then we will get hundreds of feature maps at the end. Okay, so classification by a learning algorithm. So this is, okay, image is coming here. If I animate it this way, but it's not. So image is coming here. This is the convolution part. We apply convolution operations, and then we are like applying pulling, and then transferring to classified part, and then getting class scores, which are like predictions. So this convolution is, as you see here, I explained in the previous slides as well, extract information from images. This is like, we can call like feature extractor part. And then we have a classified part. This classified head. So how much data? Okay. This is a common question. In classical machine learning, actually deep learning started around 2006, something, yeah, around that. But until that, all people were using classical machine learning algorithms. Again, the neural network is a machine learning algorithm as well. So generally, people were using like shallow networks, and then they started to use like more like medium-level networks, neural nets, and then deep networks, really like many layers. So it understood that when having more data, these algorithms, these machine learning algorithms, all are working well, especially in these deep networks. In case of traditional machine learning algorithms, as you see here, you may not need much like data. You may like 100 or samples may enough for your application. Let's say in random forest maybe, or like in decision tree, depending on the algorithm. But in deep networks, so yeah, it's very obvious we need more data to get a high performance. So this is problematic actually. This data hungry is a problematic truth for us. Let's see how much data we need. So yeah, it looks like data is really matter for most of the algorithms, especially nets. So, but how is affecting our algorithm's performance? When we have not enough data, we probably will have a underfitting problem, which is our trained model will not work at all. It's just misclassify everything, almost everything, or most of things. This is called underfitting, when we don't have enough data. I mean, like very less data we have here. But if we have lots, is that solving our problem? No. We also need to check the all the data are balanced or not, imbalance or not. So this imbalancing between classes, imbalancing problem between classes, making another, this overfitting problem class, introducing another problem. What is overfitting? We will design a network, we will design a algorithm. It will work. It will have a very high performance when we train it. But when we test it on real applications, it just again will fail because it's overfitting. It's kind of memorizing our samples. When we train it, it's just memorize samples or images, and then when we deploy it to application field, it just will fail. So that's why, we should not have less data. We need to have more data, but we also have kind of balanced data. So let's check what we have in our hands. In these satellite images, we have, this is actually a subset of the data set, around 3,000 images, not 3,000, this is 1,000 images. I'm going to show here. These are classes. As you see here, this class 5 is really leading in numbers. It's like more than 350 something. And these class 0 and class 4 is minority classes. So we have a major class and we have minor classes, and we have like intermediate classes as well. So these may cause problem, but not always. Let's check. Okay, approach 1. If you have a class imbalance problem, this may cause overfitting, as we discussed. We just give input, and then convolution operations, and then this classifier and getting predictions. And then, as you see here, we are having very high predictions. So this is kind of like overconfidence. Since these buildings, buildings are like, we have like lots of buildings in our data set. It's just, our network is seeing that images so much again and again, and it's just memorizing. Okay, it's just like learning something. So it's focusing on buildings, and then having like overconfident confidence on these buildings. So this is one problem about class imbalance, which makes the network to have overconfidence on a specific class.
Can I ask a quick question?
Yeah.
So if we have a real data set that is mostly road or mostly building, then should we train the CNN using images, training images that have mostly building, or should we have it 20%, 20%?
You mean, increasing number of building images, right?
Yeah. So if you want to use it on a real data set that is biased, then should you train it using biased data?
No, actually, so we have actually some solutions, and I'm going to just talk about it here. One solution is just decreasing number of building images, because having very like hundreds of buildings images, which we have, let's say as you in this slide, class 0 and class 4, we have very less, and class 5 is very like big number, right? So if we go like this, we might have a problem. We might have a problem, especially with 0 and 4. So our network will not probably learn these class 0 and class 4. So this is actually overfitting. That's why we need to find some ways to treat the network in some ways. For example, not on network, on data set as well. for example, decreasing number of data and number of these classified. One solution. Increasing number of these 0 and 4 is another solution. And there are other solutions as well. Playing with like laws. I'm just really, yeah, we don't have, sorry. Okay, I'm just very quickly passing these slides. Okay, this is one approach. The other approach I believe we discussed, but just as a useful information I want to like convey you. We also should check our data set if it is what is the natural distribution of that classes. Let's say we have trees and lakes in our data set, but in nature we have like more trees than lakes, right? So this is a natural distribution. So we also like check that. In that case, having more trees in our data set might not be a problem. Yeah. So this is another. This is called like prior information. Having a prior information. But most of cases, yeah, this class imbalance. I mean, this is the first approaches. Mostly we are like taking into account. But this also, we should also like keep somewhere to, yeah, handle without problem. Okay, so there are remedies. I have like 5 minutes around. I just very quickly mention some. Just try changing your metric, performance metric. There are condition metrics. This one, the first one, ROC curve, this precision recall curve. Angel Dimitri in the afternoon, he will explain this, he will also apply this, he will show this. So we need to check which classes are, we are like misclassifying, for example, in this confusion matrix. These 0 to 5 are classes. Here, are predicted classes, left one. The bottom one are true classes. So we are comparing our predicted and true classes. The another solution is understanding, oversampling, as I explained you. Sometimes decreasing number of majority class or increasing number of minority classes by applying some, like, for example, augmentation, or in case of images, augmentation, or in case of numerical data, is sampling. Yeah, this is augmentation. We can augment this single image into like different images, like these flipped, rotated, vertical flip, and this like crop, this kind of augmentation. In this way, we can increase our minority classes. And yeah, playing with loss functions. This is a long slide. I really don't have time, but this is loss. Why we need loss? I explain again, but when you explain, this is the number of parameters we need to update. All we want a good parameter. So this loss is one of the most critical part of our whole network structure. So we sometimes tweak this loss. By, for example, changing the losses firstly. There are lots of, like, many losses, hundreds of losses maybe. Which one is more like proper for our use case? And checking the progress of training. This is very common. Training and validation error. If they are very like far away, it's also a problem. And the penalizing loss by adding like penalizing for each class, for example, this class, first class is buy, the second class is don't buy. We penalize these classes by adding some like numeric values. Introducing here. In Keras, actually, it's very easily introduced, like class weights equals class weight. Buy, for example, very less. Class of don't buy very high. So you just penalize them. And using loss functions together, this is another way. This is for like even most like complex algorithms, not for simple use cases. We are using this is most like for complex, especially in GAN. There are different losses used. So and special tricks like this total loss, can explain now, and the scaling, and trying different algorithms. Yeah, this is the algorithm. We actually use the neural network, but we can change this classification, this classified hat using like this SVM or decision tree or something. So we can change this hat. We don't need to use a neural net structure. Okay, yeah, so this is all about data exploration, but I have implementation. Actually, like 20 minutes now. So in 20 minutes, it is very long. Yeah, it's obvious there is no way to implement. But Dimitri will implement, I think, is interactively. I like his style. I was thinking the same, but we are really limited time. So what we are doing here, I just explain. You can find this file and these slides as well on GitHub.
So you can open this like we did yesterday and open collab and import from GitHub.
Okay. So firstly, yeah, these are all imports. Yeah, most like this plotting imports. Yeah. 20 minutes? No, we don't have
20 minutes?
I mean,
No,
until
50,
12.
no, 50
I
minutes
really?
late, yeah.
We still have 20 minutes.
I mean, I thought it's like 40 now, right? 42.
Oh, we have 20 minutes?
Yeah.
Lunch
Really?
is at noon, and then
Oh, at noon?
Yeah.
I think.
I'm so sorry.
Yeah, it's okay. I mean,
I think you're still good.
I see, I see.
Because it said
Because you looked like you were both worried about the time.
okay. Oh, my bad, sorry.
Okay, are we all set on this follow-up? I just explain. If you can like follow, I think you can study again after the workshop.
Sorry, but I think the schedule is different, right? Sorry, because I think the other we're starting at 1, right?
Yes,
I
on
think
the
it's
email,
11:30
email,
until 1
it will
because
end.
other people are going to come at 1 and we're
Oh.
gonna start at 1.
Okay. Yeah, you're right.
Yeah, I think so.
So what should we do?
Okay, how much time we have? Like 5 minutes?
Say,
Right?
yeah.
Because I
it's
scheduled
lunch
with
and
the other
then
half
one
to.
is-
Yeah, no,
take off
you're right.
from
It's
work, right?
But
it's
it says the
11:30.
exploratory data analysis starts at 1, right? So isn't that what you're into now?
Yeah, of course. But
Then we can do this at 1. Is that what you mean?
we're not going to do this at 1.
It's another, it's later.
Oh, okay.
Yeah. But I think we can just briefly kind of explain and people can check out. So everything that you basically explained now on your slides, you can really run top to bottom and see for yourself like all the techniques that have been used, and maybe you can just briefly go over like the sections.
Okay. Okay. The scene is okay. Can you see like?
Yeah. Just kind of conceptually. It's just command plus.
Okay, so we are importing some stuff, and then here we uploaded the data into a subset of the original data into GitHub. So when you run this command, actually it's just downloading that data to your like this drive, this collapse drive. On the main branch, I'm just download.
Maybe you don't have to. Just walk them through conception.
Okay, I see. Okay, after downloading data, so we have these files. As you see, this X string and subset, and then we load this X string here because this is CSV file, and Y string here. It's also CSV, and our class names we again like get from this annotation file, and then these are shapes, 3,000 images, and this is shape, and the 3,000 is also a shape of the original file, and these are classes. And I have explanations. You can read these explanations later. I'm just telling here this shape is we need this shape anyway, not this shape. Original image shape. So okay, let's go. I'm just converting here. This shape is 3,000 something, 3,100 something into a single image shape, like 28, 4. As you see here, I just converted to the image shape, and then we still have 3,000 labels, but with 6. What is 6? I explain later again. Let's come here. I just visualize some samples by channel. So when you are writing here 3 channel, you will see RGB images of that data set. When you change this channel to 4, you will get 4 channel altogether. These are 4 channel merged together. So these are the original images. But in Dimitri's implementation, he will apply these 3 channel. You just take this 3 channel, just only this channel 4. So near it looks like this. Okay, and then coming here, this is dataset stats. Anyway, this is for normalization. I'm basically doing here just splitting every channel and then appending them to somewhere and then taking mean of each channel. For each channel, I just calculate the mean. And I use this mean to normalize images. This is also a common step for applying something. When we have images, we need to normalize when we start our processing. You can check later again. Okay, this is after normalization. I got these. It looks a little different because normalized. This is the problem here in this image. Okay, so we have Y labels, but these labels are encoded. They looks like this, or they looks like this. This is the original Y train labels. These 0, like these numbers are one hot encoded usually. So we need to decode these numbers into the single numbers. This is very easy. I'm applying here is simple like NP argmarks, which is just getting the returning the index of maximum value. It's written here. And then after this operation, okay, I just converting these 6 like channels to like 1. Not channel, it's index. So, okay, I have these classes 0 to 5. And here I'm checking the number of each class. Maybe this is better. These 2 operations are same usually. Just put here for your easily using. So for 5 we have this much images, and for other classes this much images. I just visualize here for each class. As you see here, we have bars. So some major classes, some minor classes, and then I need to like decrease some classes. For example, this class 5 and other classes as well. And I'm taking the reference as this class 4, and then decreasing all other classes, classes to this class number of class 4, which is 24. So just getting rid of most of samples and then having really less samples, but they all like balance. But this is not good.
Not a good idea.
It's not a good idea. Very bad. I mean, this is just okay. Sorry.
So typically, you don't want to take away information.
Yeah, this is very critical part. Yeah, this is just for like visualization of number of classes. Anyway, this is undersampling. We just undersample some classes into a reference class. And oversampling we have as well. Very like this is middle long, and then this class 4 and class 0, I just generate new classes. I mean new samples, and then increase the number of this class 0 and class 4 to some level. As you see here, like this looks like more balanced, right? But still, 5 is very much. So anyway, this is numeric. This oversampling is applied for numerical data, not for images. For images, we apply image augmentation, which is here. I'm getting a single image, and then applying like basic operations like horizontal flip, which is just flipping the image, and vertical flip is also flipping, but in a vertical way. And then randomly rotating image, the original image, and then randomly rotate it. And there are lots of other image augmentation techniques we can apply, and then we will have at the end more like balanced data sets. Yeah, that's
Thank you.